To continue, now we have to Professor Diego Souza introduce to Professor Isabelle Gallagher. You can start, Diego.
Okay, thank you, Juan. Good afternoon, everyone. So it's a great honor to welcome and to have Professor Isabelle Gallagher as a speaker in our seminar. Let me just tell you some words about the scientific career of Professor Gallagher. Since 2017, Professor Gallagher is a full professor in mathematics at the École Normale Supérieure in Paris. Since 2019, she is the director of the Fondation Sciences Mathématiques in Paris. Her research concerning PDEs, such as Navier-Stokes equation, wave equation, Schrödinger, among others. And she has made many important progress in the understanding of the relationship between microscopic and microscopic models of fluids. Also, let me just finish, just mention that Professor Gallagher has received numerous awards, including the Prix Paul Dr. Émile Boutet in 2008, and the Prix Sophie Germain of the French Academy of Science in 2018, and the Silver Medal of the CNRS also. In 2004, she was invited speaker at the ICM, and recently, very recently, she has been awarded with the medal of the Erwin Schrödinger Institute for Mathematics and Physics. So thank you very much, Professor Gallagher, to accept our invitation. And today, she's talking about on the dynamics of dilute gases. So thank you again, and the word is yours.
Thank you. Thanks very much for this introduction, and thanks for inviting me for this this seminar. So yeah, I'll be talking about a joint work a project actually I've been working on for a long time now with Thierry Baudineau, Laure Sarimon, and Sergio Simonella. So yeah, I'm sort of tired. It's almost 8:30 here, so I hope things will be clear. Please stop me if things get a messy or not so clear. I'm also starting to get a little bit tired. So right, so let me talk about the general context of our work, and maybe just to start with one keyword in some sense of our work is irreversibility. So meaning that you can notice in everyday life that if you don't work on your room, your desk, your whatever, then disorganization appears immediately, right? I mean, you have to do something to get things to be in order. If not, just mess and disorder just increases in time. And this seems to be related to some sense of irreversibility, right? Because you don't think suddenly your room or your desk will become in good order. Just if you reverse the arrow of time, you'll see something is strange, right? Everything seems to just get worse and worse. And there seems to be an arrow of time in the way your desk, for instance, is organized. So think a little bit to our study. Let me try to explain why just by showing you this little movie, which you can find on the web, actually, on Wikipedia, I guess. And it's the Ehrenfest paradox. So let me just show you what's going on here. So you have two containers, okay, and you have lots of particles at the beginning. They're all on the left-hand side of your apparatus, and then you just let them go. And what you can see here is that the particles are essentially what they're doing is they're moving in straight lines, and then they hit the wall, right? They go back, etc., etc. And sometimes they go to the other side. And what you're counting here, not really to see the figures here, but essentially what you're counting is how many particles are on the left-hand side and on the right-hand side. Okay, and what you see is that as time goes by, initially all the particles were on the left, remember, but then gradually you have about the same number of particles on each side. Okay, it's not always the same particles, but if you look from far at the microscopic scale, you have essentially the same number of particles on each side. Now, if you imagine for a second that there's only one particle, okay, and just look at its movement in time, okay, and each particle totally ignores the others, right? Because they're actually overlapping. They don't collide one with the other, okay? But now if you imagine the movement of one particle, then that movement is irreversible, right? You can change the arrow of time. Each particle is just going in straight lines and sometimes going back and forth, but you can play the movie in one side or the other and everything will be the same. Okay, but the whole movie we just saw, you can imagine that if you start taking that whole movie and just playing it the wrong way, the other way, something is going to go very wrong, because at the end of the movie, when you go the wrong way, then the right-hand side will totally empty and all the particles will go to the left. And this does not seem reasonable from a physical point of view, right? So what's happening here is that the whole movement of all the particles is irreversible. Okay, you can't imagine for a second that all the particles will just leave one side and all goes to the left-hand side, but the movement of each particle is reversible. Okay, so that's known as a paradox. How is it that you have lots of particles that are totally independent one from the other, right? Because they don't when they meet, they don't collide, they just overlap and go, so they ignore all the others. Each movement is reversible, but the whole thing is irreversible. So how can you explain that? And one way of explaining that, which is actually quite easy, is simply probability theory. Okay, why? Well, imagine, so the first drawing here is, imagine there were only 4 particles on the whole setup, only 4, okay? In that case, what you see in this picture here is that actually, if I count the number of particles on the left-hand side, this is this number n of t as time goes by. Initially, they're all on the left, so I have 4 on the left. And then as time goes by, sometimes you still have 4 on the left, so the right container is totally empty. Sometimes I have none on the left, so that means that all the particles are on the right, and that can happen very often. Okay, sometimes you have 1 on each side, but sometimes they're all on the left, sometimes they're all on the right. On the other hand, if suddenly I take 500 particles, okay, then initially they're all on the left-hand side, and you see that as time goes by, very quickly you'll have roughly 250 particles on each side. Roughly, not exactly 250, but roughly 250. And you can wait for a very, very long time, and never ever can you imagine that all the particles will be on the left or all the particles will be on the right. Okay, and so how do you explain this? Well, this is due to the fact that at our human macroscopic level, what we see is not each individual particle and where it is, but how many there are on each side. Right? You don't know if it's particle A or particle B that's on the left-hand side, but you can see there are 2. Okay, you can see there are roughly 250. So the number of macroscopic configurations are either there are n on the left-hand side, or n-1, or n-2, or 0. So I actually have n+1 macroscopic possibilities, okay? On the other hand, the number of configurations of microscopic configurations is 2 to the n, since each particle, if I have n particles, can be on the left or on the right. So there's a huge difference between the number of microscopic configurations and the number of macroscopic. The difference between the two is logarithm. Okay, and actually the logarithm is a measure of entropy. We'll talk about entropy later on. There's a log difference between the number of microscopic configurations and the number of macroscopic configurations. Okay, so actually the problem is not totally irreversible, in the sense that if you wait a very, very long time, essentially 2 to the n, then it will happen that all the particles will be on the same side, because it can happen. There's no reason why it wouldn't happen, but the probability that that happens is very, very small. It's 2 to the -n, roughly. Okay, so now if you imagine that n is something like the Avogadro number, then you see that you have 2 to the 10 to the -10 to the 23 probability that that will happen. So it will just never happen at our human scale. So what I'm trying to say here is that something can be irreversible because we're at a macroscopic scale, but actually it's reversible at a microscopic scale. It's really a question of scaling. Okay, so why am I talking about all that? Well, simply because what I'm interested in now is the study of fluids, okay, or gases. And so a fluid or a gas is made of a huge number of particles, right? Like 10 to the 24, roughly, the Avogadro number. They're very, very small, and they're moving all the time. Even if you're in a room which is totally silent, nothing is moving, each particle is moving very, very fast, about 600 meters per second. Okay, so a gas, even at equilibrium, is made of particles that are moving very, very quickly. And there are a lot of particles. Okay. Now, if I like, I've done it actually here. I can write down the equations for each of these particles. Okay, so essentially here are the equations I'm writing are deterministic equations, Newton's laws. Newton tells you that essentially the force is equal to the mass times the acceleration. Okay, so here I've taken 0 force to make things very easy. I'll call V sub I the velocity of particle number I. Okay, and then the velocity is simply the time derivative of the position. So I'm going to locate each of my particles by its center of mass, xi. To make things as easy as possible, I'll say that each particle is just a hard sphere, okay, mass 1. So everything's as easy as possible. And so their position is located by the center of the spheres, okay? So the velocity is just the time derivative of the position. The acceleration here is 0, so that means my particles are going in straight lines. Now, in the real life, not with the experiment we did before, but in real life, when particles meet, they collide and then they jump out one from the other. Okay, so what's the relation between the outgoing velocities and the incoming velocities is given here. So omega here is a vector on the unit sphere. Okay, and this is just a usual Descartes law or Huygens principle, giving the outgoing velocities in terms of the incoming one. You don't have to remember this formula. All you can check, if you like, is that the momentum and the energy are conserved. So I'm looking here at a system where all my particles are identical. They're moving in straight lines. They're colliding as elastic hard spheres, right? So you can imagine you're looking at a huge billiards, okay, in 3 space dimensions. Okay, so all my billiard balls are going in straight lines, and sometimes they collide and they jump out one from the other just by these laws. I won't be using exactly these laws, but I'll be using at some point the conservation of momentum and energy. Okay, so I have a large number of particles. I'll call that capital N. They're very small. I'll call epsilon their diameter. And the question is there a way to extract from this huge system of equations some kind of effective equation we can use in practice? So of course, no one uses these equations, right, to model the way a gas is going to evolve in time or water or whatever. People use macroscopic equations, right, like the Euler equations or the Navier-Stokes equations. So the question I'm interested in is trying to see if there's a way to extract from this huge system of ODEs an effective equation like the Navier-Stokes equation. Okay, how do you go from the microscopic model to a macroscopic model? So one thing I haven't said is, but you can see from the previous equations, is that these equations are time reversible. If I change all velocities into their opposites, v into minus v in the whole system, and change time into minus t, everything's fine. If you film a billiards game, the perfect billiards table, then you can play the movie in one order or the other, nothing will be strange. Okay, so this system of equations is reversible. And my question is, how can you extract from this? How can you prove some theorems saying the Navier-Stokes equations, which are irreversible, by the way, are some kind of limits model, some effective model coming from these microscopic equations? So this question is due to David Hilbert in 1900. And so his question precisely was, how can you develop mathematically some limiting process which leads from the atomistic view, which we just described, to the laws of motion of continua, like Navier-Stokes or Euler? So that was the question he asked in 1900. And so there's no answer, no precise answer to that question, but I'll just try to explain here one way of attacking the problem and what kind of results have been proved. So actually, in his question, that was the question number 6, actually, in his list of 23 questions he gave in 1900, he actually suggested that the Boltzmann's approach or equation could be used to answer this question. So we'll be talking a lot about the Boltzmann equation. So let me try to explain how this equation goes. So the idea of Boltzmann is not to go from microscopic scales to macroscopic scales, but use some intermediate scale, which we call mesoscopic. Okay, and so this intermediate scale is not telling you the density of your fluid at some position, or the velocity of the fluid, some kind of average velocity of the fluid at some position and some time, but it's going to tell you the proportion of particles, which are, let's say, at some time t, in a small neighborhood of x plus dx, and a small neighborhood of v, v plus dv. Okay, so this f of txv depends on time, on the position where I'm looking, and the velocity of the particles I'm looking at. Okay, so how many particles at time t are at x with velocity v? Okay, and the idea is that if you average this quantity f with respect to all possible velocities, this gives you a function of space and time, which will be the density of your fluid. Right? If you average this function f with respect to v dv, this will give you the velocity of your fluid. Okay, and again, if you average against v squared, this will give you some kind of temperature or some kind of energy. Right? And what you expect, what Boltzmann expects, is that these quantities R, capital U, capital theta, are going to satisfy a fluid mechanics equation, like a compressible Euler equation or a Navier-Stokes equation. Okay, so these are the macroscopic quantities. This is what you can measure. Okay, but to get an equation on those things you could measure, Boltzmann suggests first to look at this density. This is going to be a probability distribution. It's going to be a non-negative integral 1 distribution. Okay, integral with respect to x and v. That will be 1. Okay, and what we hope again is from this quantity to derive fluid mechanics equations by averaging. So the equation this quantity f satisfies according to Boltzmann. So of course there's work to prove that, and I'll try to explain what can be done actually rigorously. But Boltzmann immediately gave the equation satisfied by this density f, and we call that, of course, the Boltzmann equation. So let me just explain a little bit where this equation comes from, where all these terms come from. Okay, so first to start with, we could ignore totally the right-hand side. Let's put 0 here. If you put 0 here, what you're looking at is a transport equation, and the solution to the transport equation, f of txv, is simply taking f initially, okay, and computing it at x minus vt v. Okay, so the number of particles which at time t have position x and velocity v is exactly the same number of particles which at time 0 were at x minus vt with velocity v. That's just a transport equation. Okay, but that would be true if my particles were going in straight lines. They're not. What's happening, as we saw in the picture a few slides back, is that they collide, right? They have binary collisions. So these collisions appear on the right-hand side of your equation. They're binary, so the right-hand side is a bilinear operator. Okay, that's because I'm only looking at 2 by 2 collisions. And now what the right-hand side is telling you is how you can create a particle, in some sense, at position x with velocity v. Why would there be a particle at position x and with velocity v at time t? Well, that can happen if 2 particles collide with velocities v prime and w prime, where w is chosen anywhere in Rd, okay? And if they do that, they create a particle of velocity v and velocity w. So of course the particle is the same. What's changed is its velocities. When I'm saying creating a particle, I'm just saying I've switched my velocities and suddenly I have a particle of velocity v. Okay, so I can integrate over all possible velocities w, and what I need is that I create, so these are the scattering relations we saw before, I create a particle of velocity v. Okay, but what can also happen is simply that a particle of velocity v hits a particle of velocity w for any w, so I integrate against any w. And doing that, then I've lost a particle of velocity v, because after collision, it's another velocity that comes up. Okay, so the right-hand side here is exactly telling you that you can create a velocity v by collision, or you can lose a velocity v by collision. Okay, now the last thing I need to explain here is this thing here. We call that the cross-section. So one thing I didn't say, I also integrate against all possible omegas on the sphere. Okay, and this last term here is telling you in some sense how strong the collision is. If this is 0, that means the relative velocities of my particles, okay, is orthogonal to omega, which relates the centers of my particles. If that happens, that means my particles are just going in a parallel way, so there is actually no collision. That's why I get 0 here. Okay. On the other hand, what can happen is that my particles are going head-on. I have a head-on collision. That's the strongest possible. That's the strongest possible scalar product I can have. Okay, so it's not a proof of anything, but it's reasonable to have such a term here, a cross-section, to measure in some sense the strength of the collisions. Okay, so here I'm just presenting to you the Boltzmann equation. There's no proof, and probably this may be the way Boltzmann figured out this equation. Okay, now there are two things to do. I need to understand how to derive fluid mechanics equations from this system here. And I also need to understand how to derive this equation from my particle system. Okay, and what I'm really myself interested in is deriving this equation from the particle system, but I'll try to explain it a little bit more in a few minutes. But first, I'd like just to spend a couple of minutes studying a tiny bit this equation, right? If you're given this equation, can you solve it? And what kind of function space can you solve it? This is a PDE question, okay? Given initial data, f0, is there a solution f? How long does it live, and what function space does it live? So to answer such a question, usually what you do is first to try to find some conserved quantities, okay? What are the norms of f, or what quantities on f can I compute, which I know will not blow up in finite time? That's already a first very obvious question I should ask. And as you might know, to do that, one way of doing this, actually, to find conserved quantities would be to multiply f by a function, any function. Let's say I'll call it phi. Let's say, to simplify, it only depends on v. And I'd like to know if this quantity in time, if I integrate over v, for instance, would that by any chance be, and also x, let's say, would that be 0? Okay, that's 0. That means it's a quantity that will never, ever blow up in finite time. Okay, the integral of f phi will never blow up. So that I can use to try to solve the equation. So for that to be true, since I have a transport term which will cancel this integral over x, since phi only depends on v, what I need to check is for what function phi do I have q of ff phi of v dv dx equal to 0 for any f. If that's true, if I find a function phi which satisfies this, then I will have that this quantity, at least formally, is conserved in time. So let's see when that happens. So I have this q of ff, I multiply it by phi, I wanted that to be 0. Well, you see, one thing I can do is that once I've integrated over v and w, okay, since in q I have an integral over w, I see that everything is totally symmetric with respect to v and w. I can exchange v and w, nothing will change. Okay, so actually it's the same as half of the same thing with phi of v plus phi of w. And one other thing I can do is exchange vw with v prime w prime. If I do that, then you can check very easily that this plus sign becomes a minus sign, just because of this definition, that you can believe me, please. So in the end, what I get is 1/4 of the thing I had in q of ff, and then phi of v plus phi of w minus phi of v prime minus phi of w prime. Okay, that's just using the symmetries of my collision operator. Now, for this to be 0 for any phi, when does that happen? Well, that can happen, for instance, if phi is a constant, okay? Because 1 plus 1 minus 1 minus 1, that's always 0, okay? So if phi is a constant, this is 0. Now, another case when it's 0 is if phi is equal to v, because I get v plus w minus v prime minus w prime. Remember, that's 0 because of the conservation of momentum we saw here. Okay, and you see there's another case when it's 0 is I can use the conservation of energy, right? And then I get v squared plus w squared minus v prime squared minus w prime squared. That's also 0. And actually, that's a theorem, which I won't prove, that the only cases where this is 0 is when phi is either a constant, linear in v, or the energy. Okay, and if you notice that, that means that the integral of f times a constant is a constant. The integral of f we saw actually is a constant, it's 1. The integral of f against v is constant in time. That's the global velocity of my fluid, if I integrate over x and v. And the integral of f against v squared is constant. That means the energy is constant if I integrate it over x and v. Okay, so this equation remembers the collision properties, conservation of mass, momentum, and energy. But that's not a huge conservation, right? I mean, just the integral of f, that's not really going to help us solve the equation. Or the integral of f over v or v squared, that's not really going to help us solve the equation. But it's still interesting. Another thing you can check, okay, that's an exercise for you if you like, if you choose phi formally to be the log of f. Okay, this is totally formal. Then you're going to get log of f of v plus log of f of w. That's the same as log of f of v times f of w, divided, because of the minus sign here, by f of v prime, f of w prime. Now this has a sign. Okay, if you look at the whole thing in the integral with this log, this has a sign. It's always non-negative. So if you take the time derivative of f log f, you always get something non-negative. This is the H theorem, H like entropy, actually proved in some sense by Boltzmann. The entropy always decays in time. That's what we saw in the first picture. Well, the physics entropy is the opposite of this mathematical entropy. So the physical entropy always increases. This is irreversibility. Okay, this is the fact that disorder always is created in physics. Okay, so that's interesting. You get the creation of disorder, which is nice. That's the second principle of thermodynamics. But it also shows that the Boltzmann equation is irreversible because you have a quantity which decays in time. So if I change the arrow of time, it's going to increase. Okay, so you can't change the arrow of time in your equation because something which is supposed to decrease is going to increase. So the Boltzmann equation is irreversible. And at the time, that was a big issue, a big fight between Boltzmann and Loschmidt in particular, because people were saying, Boltzmann, you claim that this equation comes from my microscopic dynamics, but the microscopic dynamics is reversible and your equation is irreversible. So that's not possible. Okay, so that was a huge issue at the time, which now is understood, but it took a while to understand that. Okay, one last comment, which is interesting also, is okay, to solve the equation, I know this quantity is going to decay, so I can try to use this quantity. One thing I can also check is what are functions f which would be constants. So to be a constant solution to the equation, that means in particular this has to be 0. Okay, it can't be decaying, it has to be equal to 0, since I have a constant. And remember, that means that q of ff times log f has to be 0. That means that log f has to be either a constant, v or v squared, and since f is integrable, that means that f has to be a negative exponential of v squared. Okay, essentially up to translations and dilations. So these are called Maxwellians, m here as a Maxwellian. This is a constant solution to the Boltzmann equation. It cancels the dt, it cancels the v gradient x, and it cancels q of f. You can check that just because of conservation of energy. Okay, so it's also interesting to use this information, saying maybe I can solve the equation close to such a guy, because this is a global solution, since it just satisfies each term of the equation separately. So considering all that, people have been working on solving the Boltzmann equation, and here are two typical results. Result number 1, if your initial data is under control by a Gaussian, actually, then you can solve uniquely the equation locally in time. Okay, the local in time is due to the fact that this is going to get worse and worse in time. For instance, if you change the 2 into the 4, or 2 is going to get 8, 16, whatever, things are going to get worse and worse. At some point, you just can't go on. Okay, so this control is going to get worse as time goes on, and so you have a time for which you can solve uniquely the equation. If your solution is close to a Gaussian, okay, not just bounded by a Gaussian, but equal to a Gaussian plus epsilon in some sense, then the solution is global. So it's unique and global if you're close enough to a stationary solution. This is a typical nonlinear PDE, evolution PDE result. If you just have a bound, then you have a local time unique solution. If you're close to a trivial solution, you're a Maxwellian, then you have a global solution. Okay, now if I want to use entropy, if I want to have a global solution for all times, I should use entropy, right? Because this never blows up. That was done by Pierre Guillons, whom we just saw, and Ron de Perna many years back also. So yeah, 89, Ukai was 74. Using the entropy, you're not able to prove the existence of global entropy, finite entropy solutions. You can only prove the existence of renormalized solutions, a little bit worse than distribution solutions. You don't know that they're unique, but you can prove them that they're global. Okay, so that's again the usual picture. Using observations, you get global solutions, but you're not sure they're unique. And using more stronger norms, you get unique solutions, you're not sure they're global. Okay, so that's the state of the art about the Boltzmann equation. Now, I told you the Boltzmann equation converges in some sense to fluid mechanics equations. So how does that work? So the way to do that is rescale, but the free path in some sense here. Okay, alpha here is a guy going to 0. You rescale, doing that is like rescaling space and time in a hyperbolic way. You replace t by alpha t, x by alpha x. This gives you 1 over alpha. Okay, one comment here is that once you put this 1 over alpha here, the lifespan of your solution is now essentially alpha. Just like if you solve dtf is equal to f squared, the lifespan is 1 roughly. If you have a 1 over alpha f squared, then the lifespan is alpha, going to 0 with alpha. Okay. Now, if you do that, then your solution f depends on alpha. You can start computing the integrals I told you before. Integral of f against v dv, v squared dv. These things will converge in some sense to fluid mechanics equations. Let me make this precise. So you have your molecular dynamics we saw before at the very beginning. You're going to let the number of particles go to infinity while their diameter goes to 0. Okay, and you're going to let this alpha going to 0. The claim is to go from molecular dynamics to hydrodynamics. How is that? Well, you're going to scale things in such a way that roughly 1 particle, okay, in time 1, okay, if you look at the volume it's going to occupy, it's roughly, okay, in time t, in velocity v, it's going to be tv times epsilon d minus 1, because epsilon is the diameter of my particle. Okay, up to some constant, that's the volume occupied by my particle. Now, if I want to be sure that in time 1, my particle here has crossed another one, what's the probability of that? Well, I have n minus 1 particles around me. Okay, so if I want my particle to cross another particle in time 1, that means this has to be roughly equal to 1. Okay, now if my mean free path is 1 over alpha, this has to be 1 over alpha. This has to be 1 over alpha. This is known as the Boltzmann grad scaling. Okay, and that's the scaling we're going to follow. N goes to infinity, epsilon goes to 0, alpha goes to 0, and they're related by this relation, okay, which defines the mean free path. Question, one comment first, you see this is a dilute gas because N times epsilon d is very, very small. That's why my talk is called dilute gases. Okay, and then N times epsilon d minus 1 is very large, since it's 1 over alpha, and alpha is going to 0. Under the scaling, you hope to get hydrodynamics. Actually, almost nothing is known unless you put some noise in dynamics, unless your dynamics is not deterministic, but has some kind of noise, like when 2 particles meet, their velocities are exchanged in a random way. I don't know how. Okay, adding noise helps in some sense. And there are many theorems from the 90s and some a bit more recent saying that you do recover, for instance, the Navier-Stokes equations in this type of scale. Okay, I can say more if you like, if you want to know more. But for the moment, let me just summarize things in this way. I don't know. No one knows what happens from the Newton's laws I showed you before. The only thing that's known is if you add some noise to the dynamics. Okay, we don't want to do that. We want to go from Newton to Navier-Stokes. So we don't want to use extra noise. So we're going to use the Boltzmann's equation. Okay, so we're going to do things in 2 steps. First step, let me fix alpha. Okay, for the moment I fix alpha and I use the scaling I told you before. Okay, so I let n go to infinity, epsilon go to 0, fixing alpha. I want to derive Boltzmann. Second step, I have Boltzmann, I have this 1 over alpha on the right hand side, I let alpha go to 0, I want to get hydrodynamics. That's the plan, okay, in 2 steps. First get Boltzmann with fixed alpha, then let alpha go to 0 and get fluid mechanics. How can I hope this to be true? Well, because it's known, and there are many results on this, that if you take the Boltzmann equation I showed you, you let alpha go to 0, then you do recover the compressible Euler equations or the incompressible Navier-Stokes equations. So I'm not going to state any theorems here for lack of time, but you can just believe me that this works. Okay, there are lots of theorems in different settings, either renormalized solutions, strong solutions. And so there are many theorems going from Boltzmann to Navier-Stokes, for instance. Okay, so the question now is how can I do the first step? How can I do the first step going from particles to Boltzmann? And so this is known as Lanford's theorem. Let me just try to show you how it goes. The idea is to say, I start with my particle system with n particles, okay? And I look at a distribution function, meaning the probability, in some sense, that all my positions are at xn, which is x1 up to small xn. Okay, so I call that capital Xn. Capital Vn is small v1 to small vn. So this capital Fn is telling me how many particles at time t are located at x1 xn with velocity v1 vn. And this obviously, if you think a little bit, satisfies this transport equation. Okay, because my particles are going in straight lines. The only thing that can happen is that they collide. Colliding means that actually this transport equation is set in a phase space saying that my particles are not allowed to collide, meaning I don't have any overlap for my particles. Xi minus xj has to be larger than epsilon, which is the diameter of my particles. Okay, and so this equation is written down in a domain with a boundary, so I need to put boundary conditions which are given by the scattering of my particles. If two particles get very close, xi minus xj is equal to epsilon, then if they're going out one from the other, okay, touching with velocities going out, I have to replace the outgoing velocities by the incoming ones given by the scattering. Okay, it's a boundary condition for a transport equation in a domain with boundaries. Right, so for the moment, everything is essentially given by my microscopic dynamics. And if I look at not yet macroscopic point of view, but if I look at all the particles at the same time, I get this transport equation. Now, to get the Boltzmann equation, what you're going to do is to project everything into a very much smaller phase space, which is a one particle phase space. Okay, so x1, v1 here are living in, let's say, for instance, the torus. If x is in the torus, it's just the position of one particle, and v is going to be in the whole space. So the idea of Boltzmann is to say, take your huge phase space and project everything against, well, all the particles except for one. Okay, and Boltzmann's claim is that this guy here, this one particle distribution function, is going to converge to a function as n goes to infinity, epsilon goes to 0, and this function should satisfy the Boltzmann equation. Okay, so that's a way of reducing everything from a huge linear system of n particles to, if the theorem is true, to a nonlinear equation posed in a very much smaller phase space, okay, which is this here. Okay, so the theorem due essentially to Lanford is the following. Assume that initially all your particles are IID according to F0, meaning that each particle lives according to F0. Okay, its distribution is F0. The only correlation between my particles is that they don't overlap. Okay, apart from that, they're just distributed according to F0. Then this one particle correlation function does converge in the limit we gave before, uniformly towards the solution of the Boltzmann equation. Better than that, if I look at the n particle correlation function, which means I integrate against n plus 1, n plus 2 until capital N. Okay, so this is a function of small n variables. This converges to n copies of the Boltzmann solution, which means that as n goes to infinity, I have propagation of chaos. The two particle correlation function is a product of two one particle correlation functions. Okay, this is true as long as t is smaller than a constant times alpha. The same restriction I told you before for the strong solutions. If I have 1 over alpha on the right-hand side, the lifespan is alpha. So this theorem is true as long as t is smaller than c times alpha. And of course, this is a catastrophe in terms of hydrodynamical limits, because remember, afterwards, I need to take the limit alpha going to 0. Okay, and now I'm told the Lanford theorem is only true for time alpha. So if I want to go on with hydrodynamics, I let alpha go to 0, and Lanford's theorem just doesn't exist anymore. Okay, so that's exactly the reason why to this day no one knows how to go from particles to fluids, because no one knows how to improve Lanford's theorem. So let me just say a few words about that. First thing I want to say is, how come, how do you prove this result? I'm not going to prove this result at all. Anyway, time is going. I soon have to stop, I guess. But the idea, right, is propagation of chaos. Propagation of chaos means that particles become independent. Okay, the two particle correlation function is a product of two times the one particle correlation function. Propagation of chaos is independence, right? So Boltzmann actually stipulated that. He said, I assume particles become independent as n goes to infinity. I find my equation. Blandford proved it. Blandford proved propagation of chaos. And how can you expect propagation of chaos? The only way of proving that is to say that if two particles meet, they've never met before. Because if they've met before, they're correlated. So there's no propagation of chaos because they're correlated. Okay, so Blandford is able to prove that when two particles meet in some time, then they've never met before. They're independent, and not only that, but even they've never met particles. They've met particles. They've met particles. They've met before. Okay, so their collision history. They've met lots of particles in the past. Okay, but their collision histories have to be totally disjoint. Each particle has had lots of collisions before, time t, but never with particles that met in some way before. Okay, and you see when I say that, so we call that recollisions. Okay, so when two people meet, their collision trees up to there were totally independent, and actually they'll never meet again. Okay, to eliminate recollisions, you see we have decided on the arrow of time, because I keep saying before, I give myself a time t, and my collision histories have to be independent in the past. And talking about the past means I'm deciding on some arrow of time, means in some sense, Blandford's proof is irreversible. You started with a reversible system, you arrive to an irreversible equation, because in doing so, you have decided on the arrow of time. So actually with Thierry and Lauren Sergio, we wrote down a statement of Blandford's proof and a proof of Blandford, which really shows in what way it's irreversible. Okay, just one comment here. So there is averaging somewhere. What's the averaging? Well, the only thing I don't know is F0, which is the initial data of Boltzmann afterwards. Okay, so the averaging procedure means I've taken n going to infinity, but I don't know where my particles are. All I know is their distribution F0. What we do now, Blandford did do that, but for the reasons which I won't be able to explain now, you can also average on the number of particles, which makes sense because no one knows exactly how many particles there are. And so what I'd like just maybe to tell you now, I won't be talking about proofs at all for lack of time, but just one comment here is that, as I told you before, our huge problem here is letting alpha going to 0. Okay, so that does not work. I cannot do that because Blandford's result breaks down. But there are some situations where you can do that. And I'll just maybe finish here because I guess I should stop in a couple of minutes. But let me just tell you what has been done recently, or a little bit recently. That was with Thierry and Laure, where we tried to do better than Blandford in some easy settings to get fluid mechanics. So that what we really want to find is Navier-Stokes. That can't be done for the moment. So the first thing we did was say, okay, let's assume that all my particles are at equilibrium, which is totally trivial. There's nothing interesting here. But let me just assume that 1 or 2 or 3 maybe, or a finite number of particles, let's just say 1, is tagged, meaning that I'll take one particle and, for instance, let me change its position or change its velocity, just do something to it. Okay, so that is no longer at equilibrium. And then I let the system go. So initially, everyone is at equilibrium except for one particle. And let me just then let the system go. Then what happens is that you can prove that as n goes to infinity, so all the other particles, their number is going to infinity, with always epsilon going to 0, then what you get at the limit is a Boltzmann equation, which is linear. So let me maybe write it down. You get sorry, whoops, that was bad. I didn't want to do that. So if I write that down, again, okay, I write it down, I get dtf plus v gradient xf. This is the linear Boltzmann, this is the Boltzmann equation. Instead of having q of ff, right? So q of ff, remember, was something which I could write as, okay, q of ff, oh, this is gone. Let me try again without messing everything up. I used to have q of ff, which was roughly f of v prime, which I'll call f prime, f of, okay, maybe I should write it correctly. I had f of v prime, f of w prime, minus f of v, f of w, okay? That was the original Boltzmann equation. Now, let me just remove this. What I'm gonna find in this limit where I have just one tagged particle is only, if I linearize that against a Gaussian, I should have 4 terms, right? If I linearize a bilinear term. But here I only keep the following. So that's just the theorem that tells you that. Okay, times the cross section. Okay, so that's the theorem. If you let n goes to infinity, the distribution of my tagged particle is going to satisfy this linear Boltzmann equation, which is well posed, it's very easy to solve in L infinity. And now if I put a 1 over alpha here in front, and I let then alpha go to 0, I want to do the second limit, what I'm going to get is a Brownian motion for my particle. And as far as PDEs are concerned, I'm going to get the heat equation. So the heat equation is essentially the easiest fluid mechanics equation you can think of. Okay, so what you get by this theorem is exactly what I hoped. Okay, I can go from particles to fluids, but the fluid equation I get is the easiest one you can come up with, the heat equation. What's interesting in some sense in this result is that you started with a totally deterministic equation, system of equations. You take this particle number 1, you move it around in some way, let it go. At the limits when the n other particles go to infinity, their number goes to infinity and alpha goes to 0, the mean free path goes to 0. This particle number 1 is satisfying a stochastic equation, the Brownian motion. Okay, so it was sort of interesting to get a stochastic equation starting from a totally deterministic system by this procedure of limiting procedure. So that's one case where we could do the whole process. Actually, what happens to do everything, what you really do is scale alpha with n, and you decide that alpha is going to be something like 1 over, I sort of forgot, but log n, I think. Okay, so you do the whole limits maybe to some power 1/2 or 1/4. So you do both limits at the same time. Okay, so you take n times epsilon d minus 1 of the order of this log n, so 1 over log n, and everything works. So it goes to 0 very slowly, right? But it still works, and you get a fluid mechanics equation. Once we were done with that, we tried to do a bit better, and we tried to linearize a bit better the equation, saying instead of saying one particle, everyone is at equilibrium except for one particle, we said let's assume that all the particles are in some sense perturbations of the equilibrium of M. Okay, so it's a kind of fluctuation theorem. All my whole system is a little bit of fluctuation of the equilibrium. In that case, what you get is the linearized Boltzmann equation, not exactly the linear one, but the linearized, meaning I get the 4 terms on the right-hand side. Remember before, is that still there? Yeah, before, yeah. I had 2 terms, okay? I didn't have the cross terms, which would be m of v prime f of w prime minus m of v f of w. Okay, that's not exactly a linearized equation. If you do really the fluctuation results, then you get the linearized Boltzmann equation, all 4 terms. And then you can let alpha go to 0 slowly with n. I think it's 3 logs this time. And then you really get something which looks more like fluid mechanics. It's not the Navier-Stokes equations, it's the Stokes equations, okay, which are just you take Navier-Stokes and you kill all nonlinear terms. Okay, and you also get acoustic equations, which are also, in some sense, fluid mechanics equations. And that's, to my knowledge, the only cases where the whole program works, but it's totally linear problems for the moment. Okay, so I guess maybe I should stop. I'm not sure at what time I started, at what time I should stop. But if it's time to stop, then I will stop. And I'm, of course, happy to take any questions if you have some. Thanks for your attention.
Okay, so thank you very much, Professor Gallagher, for this very nice talk. So now we open the turn for questions or comments. So if anyone has some question, please open your microphone and ask the question directly to Professor Gallagher, or type your question in the chat. Professor, in your models, you do not have boundary conditions, right?
That's right.
Okay. So how could you influence the behaviors of the particles in order to attain some desired configuration. Is it possible to force?
Right, so that's a good question. So actually, there are several things you can do. What's interesting, what you're pointing out here, is that if I want to obtain some given equation, like if I want to obtain Boltzmann, I should take all my particles identically distributed. If I want to obtain the linear Boltzmann, I have to do something else. So the only thing I can play with is my initial data. Right? I'm given a particle system. The only thing I can play with is the initial data or the boundary condition. I agree with you. So let me just talk a second about the initial data. So what I'm saying here is that the only leverage you have for the moment, if I'm in the whole space or the periodic case, is the initial data. And you see that depending on the initial data, I'm going to get different equations. I can get Stokes-Fourier, I can get heat, just because I've chosen the way I just start my model, and I let the model go. So it's a good comment that maybe another way of doing that would be playing with the boundaries. The thing is, Lanfear's theorem in the presence of boundaries is extremely difficult. Almost nothing is known. The reason for that is recollisions I talked to you about, right? What you want to do to prove Lanfear's theorem is to say if two particles collide, then I'll never see them again. Sorry, then they haven't met before. Okay, that's or their collision trees in some sense I haven't defined are totally independent. But if you have a boundary, that means that I have to do this kind of analysis. I have to prove that recollisions go to zero as epsilon goes to zero. Although particles will collide with the boundary, so it's much harder geometrically to prove that if two particles meet, they haven't met before, because of the boundaries, things very difficult could happen. So that has been done in a half space by Théophile Dormer, one of my students. He's also working on the exterior of a convex domain, but a general boundary is really very hard. The only thing that can be done, I guess, is, for instance, if you start putting noise on the boundary, like when a particle hits the boundary, then maybe its velocity is going to be diffused in some random way. Then you can do things and find other equations too, right? But that's essentially the only things I know about this question. It's a good question.
Okay, so thank you. Is there any other question?
Yeah, can I ask a question?
Yes. Okay, go ahead.
So yeah, this boundary question is interesting, and do you expect to have hopefully a non-slip boundary condition as a limit? I mean, what would be your guess? I mean, is the right one? Is it the right one?
Yeah, so from what I know, it's not things I've done myself, but you can derive Navier-Stokes with a no-slip boundary condition from the Boltzmann equation. Okay, that was done, I think, by Laure and Nader-Mismoudi, among others. So yes, I'm pretty bad with boundaries. So I'm not sure. I'm very scared when you give me boundaries. I get scared. So I don't know much about the literature here, but I think, depending on the way you fix things for your Boltzmann equation, if you put totally specular reflection, or you start putting a bit of diffusive, a bit of something else, then you can get other limits, like Robin limits and that kind of thing for Navier-Stokes. So from Boltzmann to Navier-Stokes, things are understood in some sense. So you can play with your Boltzmann boundary condition to get different boundary conditions and limits. But I don't know, honestly, I don't think anything has been done from the particle system to the Boltzmann equation with boundaries. Right?
Okay, thanks.
It's really not really well known.
Okay. And yeah, if I may, so maybe I missed the viscosity. How does the viscosity would come up in the Navier-Stokes?
Yeah, it's a very good question.
From Boltzmann, yeah.
Yeah, it's actually the same. You can even wonder maybe how the heats arise, why there's a second order term, right? It's the same. It's essentially the same reason. So maybe I can explain that in just in a few lines if I can. I'll try. So what you do is you start with your. I'll do that here. You start with Boltzmann, right?
Right.
And then so you rescale everything. So you have this 1 over alpha, and actually I cheated to do a bit more than that. You're going to rescale time again. So we call that a diffusive limit. Okay, and that's why diffusion appears. So I wait for even longer time. So I didn't tell you that, but to get the heat equation, not only do you do alpha to go to 0, but you also rescale time. You replace t by alpha t. So t has to be now very, very large to see anything. So that means, in other words, you're doing something like that in your equation. You have a square in front of q of ff and a 1 over alpha against the transport. And now what's going to happen is that since you have an alpha squared, if you want to get the limits alpha going to 0, first thing you're going to do is assume this has to be 0 to kill the 1 over alpha squared. But then you have a v gradient here. And if one way of explaining things maybe is that to kill all that, you have to go to the second order in alpha in your, if you say f converges to something, okay, then to kill all those alphas and alpha squares, you have to understand the second order in terms of a kind of decomposition in terms of alpha, which means you have to apply this twice. Okay, I'm not really proving anything here, but it's very sketchy, but essentially it's really what happens technically, right? You want a second order, so you have to apply this twice, and then you get a diffusion, okay, because you have a gradient twice. So that's how you get a heat, and that's how you get Navier-Stokes.
Okay.
But again,
thanks.
that's because you wait for a long time. If you don't do that, you get Euler. Don't have any diffusion.
Okay. Okay. Nice. Thanks. Nice. Very nice.
Okay, is there any other question or comment? So if not, let us thanks again, Professor Gallagher, for this very, very nice talk. So thank you very much.
Thank you. Thanks for inviting me. Have a nice day.
Thank you, Diego. Thank you a lot, Professor Isabelle Gallagher, for your amazing talk.
Thanks very much.